Hello! In this video, we're going to be looking at some example problems involving proofwriting. It's pretty much just going to be some exercises on basic set theory and basic problems involving the real numbers. These problems come from Daniel Velleman's book, How to Prove It. So let's start with this problem. Suppose x and y are real numbers, y plus x is equal to 2y minus x, and x and y are not both 0. Prove that y is not equal to 0. So we're trying to prove y is not equal to 0. So what do you think we could do to show that? Well, let's try to prove it by contradiction, right? Well, what if we assume for a contradiction that y is instead equal to 0? The reason why that might be a good idea is because if y is equal to 0, well then, since this equation is true, we just substitute y for 0. And that will be true as well. It might give us something to work with to reach a contradiction. So, if we reach a contradiction, that will tell us that our assumption that y is equal to 0 was wrong. So we must instead have that y is not equal to 0. So, let's do some scratch work. So, what happens if we assume that y is equal to 0? Well, let's write down this equation, which we know it's what we're given. Right, since y is equal to 0, we could substitute y for 0. So we get 0 plus x equals 2 times 0 minus x. We know that tells us x is equal to negative x. We just add x to the other side. We get 2x equals 0. But then you just divide 2 to the other side. We see that x is equal to 0. Okay, but so what? Well, let's look at the other thing that we're given. We're given that x and y are not both 0. In other words, we're given that it is not the case that both x and y are equal to 0. But we've just showed that both x and y are equal to 0. And that contradicts the fact that they're not both 0. We've reached a contradiction, right? The fact that x is equal to 0 and y is equal to 0 contradicts this fact that we are given. So, we've reached a contradiction. So, our assumption that y is equal to 0 leads to a contradiction. So we must instead have that y is not equal to 0. So we're ready to write up the proof. Right, the proof is proof by contradiction. We will write out, assume for a contradiction, y is equal to 0. And from here, we will reach a contradiction. So, let's start out. Since this equation is true, we were able to substitute y for 0, because y is equal to 0. So we get this, but the left-hand side is just x, the right-hand side is just negative x. So we have x equal to negative x. All right, I'm just going to write x equals negative x. Then we add x to the other side, so we get 2x equals to 0. So I'll say thus, 2x equals 0. Then when we divide 2 to the other side, we see that x is equal to 0. So I'm going to write so x is equal to 0. Right? It's understood that we algebraically obtain x is equal to 0 here. So now we're going to emphasize we have deduced that x is equal to 0 and y is equal to 0. Which contradicts our hypothesis that x and y are not both 0. So we've reached a contradiction. Our assumption that y is equal to 0 led us to a contradiction, so we must instead have that y is not equal to 0. So I'm going to write therefore, y is not equal to 0. So that's it. This completes the proof. So now let's look at another example problem. Suppose x and y are real numbers. Prove if x squared y is equal to 2x plus y, then if y is not equal to 0, then x is not equal to 0. So we're trying to prove a conditional statement, right? The overall conditional statement that we're trying to prove is if this is true, then this is true. Right, and the standard way we can prove a conditional statement is we make the assumption that this is true, and we try to logically deduce that this is true. So for our scratch work, that's what we're going to do. Right? Let's make the assumption that this is true. From here, we're going to try to logically deduce that this statement is true. Now again, we're trying to prove another conditional statement. So the standard way we could do it is we could try to make the assumption that y is not equal to 0. From there, try to logically deduce that x is not equal to 0. Now, we could do it that way, but let's think of another technique that we could use to prove the statement. Another technique we can use to prove the statement is to prove the contrapositive. The contrapositive tells us that this statement is equivalent to saying if this is false, then this is false. Or in other words, this is equivalent to saying if x is equal to 0, then y is equal to 0. These two statements are equivalent. So if we can prove this statement, that means that we have proven this statement. Let's try to prove this statement, because it might be nicer if we prove this statement, because, well, to prove this statement, we would make the assumption that x is equal to 0 and try to logically deduce that y is equal to 0. Right? So let's make the assumption x is equal to 0 and try to logically deduce y is equal to 0. The reason why this might be nicer is because now, since we know that this equation is true, we can substitute x for 0. Now we'll see what happens. Well, notice if we substitute x for 0 in here, the left-hand side becomes 0 squared y. The right-hand side is 2 times 0 plus y. Right, but that's 0. This is y. So we get y equal to 0. If we just plug x in for 0, this simplifies down to being y equals 0, which is exactly what we wanted to deduce. So, under the assumption x is equal to 0, we've logically deduced y is equal to 0. So that means we've proven this statement. Because this statement and this statement are equivalent, that means we have proven this statement. So I'm going to say, under the assumption x equals 0, we've logically deduced y is equal to 0. So in other words, we've proven if x is equal to 0, then y is equal to 0. But because this statement is logically equivalent to this statement, that means we have proven if y is not equal to 0, then x is not equal to 0. So we've proven this statement. So if we make the assumption that x squared y is equal to 2x plus y, we've logically deduced that this statement is true. So we've proven if x squared y is equal to 2x plus y, then this is true. So that proves this conditional statement. We're ready to write up the proof. So, the start of the proof, we're proving this conditional statement, and we make the assumption x squared y is equal to 2x plus y. And from here, we'll try to logically deduce that this statement is true. And the way we did that in our scratch work was, we proved the contrapositive. So, in the proof, I'm going to note that we're proving the contrapositive of this statement. And that indicates that we're going to be proving this statement. So, to prove this statement, we'll make the assumption x is equal to 0. So assume x is equal to 0. From here, we're going to logically deduce y is equal to 0. Well, what we did in our scratch work was, since x is equal to 0, we just substitute x for 0 in this equation. So we get this, but then the left-hand side is 0. The right-hand side is 0 plus y, which is just y. So we see that y is equal to 0. So we've logically deduced y is equal to 0. So what we've done here is, we have shown under the assumption that x is equal to 0, it follows that y is equal to 0. And that means we've proven this statement. We've proven if x is equal to 0, then y is equal to 0. And so I'm going to write down that we've proven this statement in our proof. So we've proven this statement, but that's logically equivalent to this statement. So because we've proven this, that means we've proven this. I'm going to write that down in our proof as well. So that means if y is not equal to 0, then x is not equal to 0. So that's it. Putting this all together now, we have shown under the assumption that x squared y is equal to 2x plus y, it follows if y is not equal to 0, then x is not equal to 0. So that means we've proven this entire conditional statement. And so I'm going to write that down in the proof as well. So that's it. This completes the proof. So now let's look at another example problem. Suppose x and y are real numbers. Prove if x is not equal to 0, then if y is equal to 3x squared plus 2y over x squared plus 2, then y is equal to 3. So again, we're trying to prove a conditional statement, which says if this is true, then this is true. And the standard way to do that is we'll make the assumption that this is true and try to logically deduce that this is true. So let's make the assumption that x is not equal to 0. So scratch work, make the assumption x is not equal to 0, and we'll try to logically deduce that this statement is true. Now again, we're trying to prove a conditional statement. And to do that, what we can do is we'll make the assumption that this is true, try to logically deduce that y is equal to 3. Right, so we'll try that standard technique. So we'll assume that this equation is true. We'll try to logically deduce that y is equal to 3. The reason why doing it this way might be useful is because, well, maybe we could reduce this equation down to y equals 3. Because, well, notice if we multiply x squared plus 2 to the other side, what do we get? We get this, but then if we distribute the y across, what happens? You get this, but then 2y appears on both sides of the equation, so you could subtract them and cancel them out. You're left with x squared y equals 3x squared. So then we see x squared appears on both sides, so we should be able to divide x squared on both sides, right? Since x is not equal to 0, that means we can divide x squared. So if we divide x squared on both sides, what happens? X squared y divided by x squared is just y. 3x squared divided by x squared is just 3. So we're left with y equals 3, which is exactly what we want. So, doing it the standard way, we're able to reduce this equation to saying y equals 3. So we're done. We have a proof of this. So, to write up the proof, overall we're proving this entire statement. Right, the way we're doing that is we make the assumption that x is not equal to 0. So assume x is not equal to 0. From here, we're going to logically deduce that this statement is true. Right, and again, we're proving a conditional statement. The way we do this in our scratch work was we make the assumption that this equation is true. Then we logically deduce y equals 3. So assume this equation is true. Now, it seems like I'm going to be writing assume here twice, right? Which might look annoying. So instead, in the proof, I'm actually going to write, to prove if this is true, then this is true, assume this is true. You don't have to add these extra words if you don't want to. You could just write assume this equation is true. It's still going to be logically correct, but I think this just looks nicer. So we assume this is true, and we're going to logically deduce now that y is equal to 3. So the way we did that was we multiply x squared plus 2 to the other side. So we get this, but when we distribute the 2 across this parentheses, we get x squared y plus 2y. So we see that 2y appears on both sides of the equation, so we can cancel all of them out. We'll get x squared y equals 3x squared. So I'm going to write so x squared y equals 3x squared. Now at this step, we divide the x squared on both sides. And I'm going to say that we can do that because x is not equal to 0. So I'm going to say since x is not equal to 0, we can cancel the x squared to obtain y equals 3. So that's it. What we've shown here is, under the assumption that this equation is true, we've logically deduced y is equal to 3. So that means we've proven if this is true, then this is true. So I'm going to write that down. We have proven if this equation is true, then y is equal to 3. So we've proven this statement, but we proved that under the assumption x is not equal to 0, right? So really, under the assumption x is not equal to 0, we've logically deduced that this statement is true. And therefore, we've proven this entire conditional statement. So I'm going to write, therefore, this entire conditional statement is true. And that's it. We've proven exactly what we wanted to prove. So this completes the proof. Suppose A is a subset of C, and B and C are disjoint. Prove if X is an element of A, then X is not an element of B. So we're trying to prove a conditional statement. And to prove a conditional statement, the standard technique we could try first is we make the assumption that this is true and try to logically deduce that this is true. So let's make the assumption that X is an element of A, and we'll try to logically deduce that X is not an element of B. So for our scratch work, let's make the assumption X is an element of A. We'll try to logically deduce X is not an element of B. So let's write down everything that we're given. So we have A is a subset of C, and we have B and C are disjoint. Now let's remind ourselves what these two things mean. To say A is a subset of C means that every element of A is also an element of C. To say B and C are disjoint means that B and C have no elements in common. So, let's see. Can we use these givens in any way? Well, since X is an element of A, and every element of A is also an element of C, then in particular, X must be an element of C as well. So, we can obtain that X is an element of C. But then what about this given? Well, since B and C are disjoint, this means B and C don't have any elements in common. So in particular, it can't be the case that X is an element of both B and C. Well, we know X is an element of C, so X can't also be an element of B. So X is not an element of B. And we've logically deduced X is not an element of B. So that proves this conditional statement. We're ready to write up the proof. So to write up the proof, we prove this by making the assumption that X is an element of A. So to start the proof, we will say assume X is an element of A. From here, we will logically deduce that X is not an element of B. Well, following what we did in our scratch work, since X is an element of A and A is a subset of C, that implies X must be an element of C. But then, how did we reach X is not an element of B using the fact that B and C are disjoint? So, since X is an element of C and B and C are disjoint, then X can't be an element of B. And that's it. We have logically deduced what we wanted to logically deduce, which is that X is not an element of B. So we've proven if X is an element of A, then X is not an element of B. So this completes the proof. So now let's look at another example. Suppose A set minus B and C are disjoint, and suppose X is an element of A. Prove if X is an element of C, then X is an element of B. So again, we're trying to prove a conditional statement. So let's first try to prove it the standard way. Right? We'll make the assumption that X is an element of C, and we're going to try to logically deduce that X is an element of B. So for our scratch work, we'll make the assumption X is an element of C. We'll try to logically deduce that X is an element of B. Let's write down the other things that we're given. We're given that A set minus B and C are disjoint. We're also given X is an element of A. Now let's remind ourselves A set minus B is the set of all elements which belong to A and don't belong to B. So, let's see. What can we deduce from this? Well, noticing that X is an element of C and a set minus b and c are disjoint, well, these two sets share no elements in common. Therefore, x can't be an element of a set minus b. So, x is not an element of a set minus b. So then how can we use what we're given here and try to deduce that x is an element of b? Well, if you can't see it right away, let's try a proof by contradiction. We're going to make the assumption that x is not an element of b, reach a contradiction. Because we reach a contradiction, our assumption that x is not an element of b was wrong. Therefore, we must instead have that x is an element of b. So, we assume x is an element, or x is not an element of b. We're going to try to reach a contradiction from this assumption. Well, notice this is useful because we see x is an element of a and x is not an element of b. Therefore, that means we would have that x is an element of a set minus b. So we have x is an element of a set minus b, right? That's because we would have x is an element of a and x is not an element of b. That's how we get this. So we see that x is an element of a set minus b and x is not an element of a set minus b. That's a contradiction. So we reach a contradiction if we make the assumption that x is not an element of b. So our assumption that x is not an element of b was wrong, and therefore we must have that x is an element of b. And that's exactly what we wanted to deduce. So we're ready to write up the proof, right? We can prove this conditional statement. So to prove this conditional statement, we make the assumption that x is an element of c. So assume x is an element of c. From here, we'll logically deduce that x is an element of b, following what we did in our scratch work. So, using the fact that a set minus b and c are disjoint, well then, since x is an element of c, x can't be an element of a set minus b. Now, to show that x is an element of b, we assume for a contradiction that x is not an element of b. So then how do we reach a contradiction? Well, since x is an element of a and x is not an element of b, that means by definition that x is an element of a set minus b. So now we see that x is an element of a set minus b and x is not an element of a set minus b. So we have a contradiction. So our assumption that x is not an element of b leads to a contradiction. So we must instead have that x is an element of b. And now putting this all together, we see under the assumption that x is an element of c, we can logically deduce that x must then be an element of b. So we've proven if x is an element of c, then x is an element of b, as required. And so this completes the proof. So now let's look at one more problem. Prove it cannot be the case that x is an element of a set minus b and x is an element of b set minus c. So we're trying to prove the negation of a statement. So naturally, maybe you want to try proof by contradiction. So assume for a contradiction that it instead is the case that x is an element of a set minus b and x is an element of b set minus c. So for scratch work, let's see, what if we make the assumption that it is the case x is an element of a set minus b and x is an element of b set minus c? Well then, by definition, this means x is an element of a and x is not an element of b. By definition, this means that x is an element of b and x is not an element of c. So now looking at what we have here, we have deduced x is an element of b and x is not an element of b. So we have a contradiction. So, assuming that it is the case that x is an element of a set minus b and x is an element of b set minus c, will lead us to a contradiction. Therefore, since our assumption leads us to a contradiction, we must instead have that it is not the case that x is an element of a set minus b and x is an element of b set minus c. So we have a proof. It's just going to be a proof by contradiction. So to write up the proof, we first say, assume for a contradiction that it is the case that x is an element of a set minus b and x is an element of b set minus c. Well, then let's look at what we deduced in our scratch work. Since x is an element of a set minus b, then that means x is an element of a and x is not an element of b. But then, since x is an element of b set minus c, that means x is an element of b and x is not an element of c. And now we see we have x is an element of b and x is not an element of b, and that's a contradiction. Our assumption that it is the case that x is an element of a set minus b and x is an element of b set minus c led us to a contradiction. So we must instead have that it is not the case that x is an element of a set minus b and x is an element of b set minus c. And so this completes the proof. And so yeah, that's pretty much it for this video.